Welcome back. In the last lesson, we talked about validation curve, how to actually identify whether our model has been underfitting or overfitting the data based on the hyperparameters itself. And this lesson, we're going to move into learning curve. Now, the learning curve shows the validation and training score of an estimator for varying number of training samples. Now, let me just highlight this again. Learning curve shows you the validation and training score versus the number of training samples, whereas validation curve shows the validation and training scores versus varying hyperparameters. So therein lies the difference between the two. Now, really, learning curve is a tool to find out how much we benefit from adding more training data and whether the actual estimator itself suffers more from a variance error or a bias error. Now, if both the validation score as well as the training score converge to a value that is too low with increasing size of a training set, we will not benefit much from more training data. Now, I just want to go through a couple of examples so that you can see what a learning curve looks like before we look at some empirical data. Below here is an example of a good variance bias trade-off learning curve. Now, what we have is the accuracy. It can also be R-score. Now, the actual level of performance that's achieved here, which is this one here, is high. Okay, and the actual level of performance achieved is close to the desired level of performance. That's the first thing. The second thing is that the training and also tests are tight and converge to a similar level. So notice that initially, when we have low number of training or small sample size, it actually diverged, meaning there's actually a lot of, although the training accuracy was high, that's only because it sees a very small amount of data, whereas the actual test data itself has a very large error or very low score. As more and more data is fed through, the test score increases and the training score decreases, eventually converge together to a point. So what you have, this is really an example of good variance bias trade-off. And below is an example of a high bias learning curve, and where you have low training and test score. Basically, it underfits the actual training data itself. The actual performance level is far from the desired level of performance. So how do you address this? You can address this by increase the number of parameters or the features, basically adding or creating new features, or decrease the regularization, because what you have is actually a high bias here, meaning a large error. So this is the desired level of performance. What you have though is that the training converged to a level substantially lower than the desired level of performance. Likewise, the test, although it improved, it did not improve to a level that is actually sufficiently high enough to be desirable for our estimator. So this is an example of high bias learning curve. So let's move on to one that is an example of a high variance learning curve, where you have the training and the test level do not converge or converge slowly. The training and as well as the test level are still very far apart. This is really an example of overfitting. You can address this by collecting more training data or reduce your model complexity. Remember, we have 14 parameters before, so it's better to actually, 15 parameters, it's better to reduce it down to 4 in our example earlier for the polynomial. So that's really reducing the model complexity and increase regularization to avoid so-called complexity. It doesn't allow the parameters to actually gyrate wildly. Although this is the desired level of performance, what you have is that there's a large variance here. In order to converge, you actually basically have to feed a lot of data into it. The other example that I want to look at or show you here is around here is pretty much the adequate sample size. More data didn't actually really improve the performance of your algorithm or your estimator that much. Right, enough of the theory. Let's look at an example. This is from scikit-learn, where the key observation, this is for naive Bayes classifier as well as for the support vector machine. Both the training score and also the cross-validation score are not very good at the end. So let me just run this and let it run at the background until the number comes up. Okay, this is done running. So, and what you have here is that the score not very good at the end. Okay, so very often what this is that the training score is very high at the beginning and decreases over as more and more data is being fed into the model. The cross-validation score start low and increases as more data is provided. Now let's look at the observations for the support vector machine. The training score is still around the maximum. The validation score could be increased with more training examples. Okay, so I won't run through the codes. This is just really to illustrate the concept here. We're going to come back to the code a little later. Okay, let's look at the naive Bayes. Remember what we have earlier is that the main point that we take away is that both the training and the cross validations are not very good at the end. Okay, so although they converge, right, this is the high bias example we talked about here, is very far away from what we're looking for, which is 1 or 100%. This converged to around 85% for the naive Bayes. And this is the support vector, and the red one is the training score. Okay, the green one is the cross validation score. Okay, so it converges to pretty good number, around probably 97, 98. In order to continue for the green line, which is really what we want here, the out of sample score is high, we can provide more data. So that's really the basic ideas of learning curve and how to make use of it. Okay, so it tells you how much data do you need to actually get a reasonable accuracy in terms of your data, and whether your estimator suffer from too much regularization or too few features. Here you can see the actual score is too low. That's basically highlight the fact that in order for it to go up, we need to actually provide more predictors or independent variables. So in terms of reading this, you have the usual NumPy and matplotlib. We imported the Gaussian naive Bayes, the support vector machine. We are doing this on the digits data, which is the handwriting data sets, and we are importing the learning curves and also the shuffle split. We'll cover shuffle split in the next video. This is really to plot the learning curve itself. Nothing really fancy here. It's just plotting the curve, splitting the the data into the train size, using the learning curve to extract the train size, train scores, and also the test scores. And this is calculating the mean and also standard deviation for both the train and also the test. And this is really the plotting of it. We've seen this before. And finally, this is actually running the code itself. Notice that there are two curves that's being plotted. You have the naive Bayes here, okay, which is this portion here, and this portion is actually plotting the support vector machine using the RBF kernel, which is non-linear. Right. Okay, so where do you want to go from here, or where do we go from here? You can read more from the scikit-learn. I'll provide a link on Machine Learning Master as well as Elite Data Science for you if you are interested to read more. Right, the exercise now is on our Boston housing data price prediction, if you recall. I want you to actually do one on learning curve and also one on the validation curve using the data, using the code that I provided earlier. This example that I am doing uses rich regression because remember that our Boston housing data set is as a continuous numerical value rather than classifier. So I'm using rich as an example and as an illustrator of how to make use of the learning curve as well as the validation curve. So I'm using rich here. Remember, learning curve is about plotting your train and also test score versus the number of samples. So that's one. And the validation curve is about varying the hyperparameters. In this case, we are varying the alpha, which is the regularization parameter. Now, I'm not going to run through this with you right now. I want you to actually try this out as an exercise. Don't pick at my code. Okay, try that out on your own. It would be really beneficial. So pause the video now, and when you come back, I'm going to walk through the codes and also the actual curve with you. I'll see you in a minute. Welcome back. How did that go? I hope you at least give it an attempt and tried it out, and hopefully you actually extracted some values out of that, just playing around with the codes, and just get a feel of how the codes are written, how to plot graph, how to actually draw a band, plus and minus one standard deviation, calculate the mean of both the test score as well as the validation score, and just plot it out. And also running through, in essence, to do this, you actually have to fit your model and use the learning curve, what do you call it, the learning curve method, or the library, there's inbuilt library, which is this one here. Okay, so all right, let's study this curve and see what it's actually telling us. The first thing is, remember, this is a learning curve, and as we increase the data, around the 250 is optimal. More data only improve the performance marginally. We see the usual shape, which is the training curves. Training score starts well, and then it decreases as you feed more data. And the cross-validation score start off poorly and improved as you increase more data. Okay, and notice too that the actual band, the one standard deviation, is really wide initially and improved over time. What do you observe here? A couple of things is that the bias is really high. Around 1 is what we're aiming for. This settle at around 70%, rather R square of 70%. So which is really rather low actually. So the bias is actually quite low. So really ideally what you want to do here is actually, again, we mentioned before, reduce the regularization. That's one. 2 is to increase or add more features. So let's look at the validation curve. I also ran it already. So what do we actually see here? We can see that a small amount of regularization, roughly about 0.1, is sufficient. Okay, and if you go any more or larger in terms of penalization or higher, the smaller the alpha, it doesn't actually seem to improve the performance that much. However, as you actually, if you basically have it as a linear regression, the performance deteriorates really substantially and very, very quickly for both the training as well as validation accuracy. I hope you found it useful in terms of a walkthrough for both the validation curve as well as the learning curve. And in essence, what we talked about really is that the learning curve is plotting both your test score as also your training score versus the number of samples. Whereas the validation score is basically varying your hyperparameters and measure that against the training and also the validation score. So as you vary your hyperparameters, it obviously will have an impact on the training and also validation. It allows you to see whether your model is overfit or underfit, and via learning curve, whether you add more data will actually improve the performance of your estimator. Right, I hope you found that what we have covered really useful. And there's a lot of concept that's being covered here. I'm going to leave that with you. It'd probably be a good exercise for you to actually try it out instead on Ridge. Try it on other estimator. You can try it on Elastinet or Lasso, as we talked about. A couple of the models that we went through before, and vary the actual hyperparameters and run through both the learning curve as well as the validation curve. See what are the things that you can actually learn from that. And I'm going to leave that now. When we come back, I'm going to go into cross-validation, in particular K4 cross-validation, to expand on that concept to help you understand how cross-validation can help you to improve your model. I look forward to seeing you in the next video.